Today we will continue with Chapter 18. We're going to start with 18.6, the effects of departures from model. In preceding sections, we considered how residual analysis and other diagnostic techniques can be helpful in assessing the appropriateness of the ANOVA model for the data at hand. We also discussed that the use of transformations for both stabilizing the variance and obtaining an error distribution more nearly normal. The questions now arise: what are the effects of any remaining departures from the model on the inferences made? So first, we're going to start with non-normality. For the fixed ANOVA model 1, the lack of normality is not an important matter, provided the departure from normality is not extreme. It may be noted in this connection that kurtosis of the error distribution either more or less peaked than a normal distribution. It is more important than skewness of the distribution in terms of the effects on inferences. The point estimators of factor level means and contrast are unbiased whether or not the populations are normal. The F-test for the equality of factor level means is but little affected by lack of normality, either in terms of the level of significance or power of the test. Hence, the F-test is a robust test against departures from normality. Single interval estimates of factor level means and contrasts and the Sheff multiple comparison procedure also are not much affected by lack of normality, provided that the sample sizes are not extremely small. For the random ANOVA model 2, the lack of normality has more serious implications. The estimators of the variance components are still unbiased, but the actual confidence coefficient for interval estimates may be substantially different from the specified ones. The unequal error variances. When the error variances are unequal, the F-test for the equality of means with the fixed ANOVA model is only slightly affected if all factor level sample sizes are equal or do not differ greatly. Specifically, unequal error variances then raise the actual level of significance slightly higher than the specified level. Similarly, the Sheff multiple comparison procedure based on the F distribution is not affected to any substantiated extent by unequal variances when the sample sizes are equal or approximately the same. Thus, the F-test and related analysis are robust against unequal variances when the sample sizes are approximately equal. Single comparisons between factor level means, on the other hand, can be substantially affected by unequal variances, so that the actual and specified confidence coefficients may differ markedly in these cases. The use of equal sample sizes for all factor levels not only tends to minimize the effects or unequal variances on inferences with the F distribution, but also simplifies calculational procedures. Thus, here at least, simplicity and robustness go hand in hand. For the random ANOVA model 2, unequal error variances can have pronounced effects on inferences about the variance components, even with equal sample sizes. Lastly is the non-independence of error terms. The lack of independence of the error terms can have serious effects on inferences in the analysis of variance for both fixed and random ANOVA models. Since this effect is often difficult to correct, it is important to prevent it in the first place whenever feasible. The use of randomization on those stages of a study that are likely to lead to correlated error terms can be a most important insurance policy. In the case of observational data, however, randomization may not be possible. Here, in the presence of correlated error terms, it may be possible to modify the model. Modification of the model because of correlated error terms may also be necessary in experimental studies. Next, we move on to 18.7, the nonparametric rank F-test. When the transformations are not successful in bringing the distribution of the error terms close enough to normality to meet the robustness properties of the standard inference procedures, a nonparametric inference procedure can be useful. Nonparametric procedures do not depend on the distribution of the error terms. Often, the only requirement is that the distribution is continuous. The nonparametric procedure considered here assumes that the R populations under study are continuous distributions that differ only with respect to location. Thus, it provides a test for differences in popular means or medians, assuming that the shapes of the populations, their variances, skewness, or kurtosis, are identical. The test procedure is very simple. All n sub t observations are ranked from 1 to n sub t in ascending order. Then the usual F-star statistic is calculated, but now based in the ranks, and the F-test is carried out in the ordinary manner. So the test procedure is that we have the Yij observations, which first need to be ranked in the ascending order from 1 to n sub t. We shall let Rij denote the rank of Yij. In the case of ties among some observations, each of the tied observations is given the mean of the ranks involved. For instance, if two observations are tied for what would otherwise have been the third and fourth ranked positions, each would be given the mean value 3.5. To test the whether treatment means are equal, the usual F-star test statistic is obtained based on the ranks Rij. This test statistic is now denoted by F star sub R, which is equal to the MSTR over the MSE, where the MSTR is the summation of Ni of Ri dot bar minus R dot bar squared over R minus 1. The MSE is the double summation of Rij minus Ri dot bar squared over N sub T minus R, and Ri dot bar is equal to the summation of Rij of all j over Ni, and the R dot bar is equal to the double summation of Rij over N sub T, which is actually equal to Nt plus 1 over 2. Note that the R dot bar, the overall mean of the ranks, is a constant for any given total number of case N sub T. When the treatment means are the same, test statistic F star R follows approximately the F of R minus 1 Nt minus R distribution, provided that the sample sizes Ni are not very small. So to test the alternatives, we have the null hypothesis equaling to the mu's being equal to each other, and the alternative hypothesis being that not all mu's are equal. The appropriate decision rule to control the type 1 error at alpha is, if F star R is less than or equal to the F of 1 minus alpha, R minus 1 Nt minus R, then we conclude the null hypothesis. And on the other hand, if F star R is greater than F of 1 minus alpha of R minus 1 Nt minus R, then we reject the null hypothesis. The multiple pairwise testing procedure. If the rank F test or the Kurzweil-Wallace test leads to the conclusion that the factor level means mu I are not equal, it is frequently desired to obtain information about the comparative magnitudes of these means based on the rank data. A large sample testing analog of the Bonferini pairwise comparison procedure discussed in 17.7 based on the ranks for the observations may be employed for this purpose, provided that the sample sizes are not too small. So we have testing limits for all G equals R times R minus 1 over 2 pairwise tests using the mean ranks Ri dot bar are set up as follows for family level significance alpha, where we have Ri dot bar minus Ri prime dot bar plus or minus the Bonferini of Nt times Nt plus 1 over 12 times 1 over Ni plus 1 over Ni prime, where we take the entire square root of the answer, where B equals Z of 1 minus alpha over 2G, and G is R times R minus 1 over 2. If the testing limits include 0, we conclude that the corresponding treatment means mu I and mu I prime do not differ. If the testing limits do not include 0, we conclude that the two corresponding treatment means differ. On the basis of all pairwise tests, we then set up groups of treatment means whose members do not differ according to the simultaneous testing procedure. In this way, we obtain information about the comparative magnitudes of the treatment means mu I. Next, we're going to go over a few problems in the text. We will start with problem 1, I believe. Yes. So refer to figure 18.3 and 18.4. What feature of the residual sequence plots enables you to diagnose that in one case the error variance changed over time, whereas in the other case the effect is of a different nature? Could you make a diagnosis about time effects from residual dot plot? So let's go back to figure 18.3 and 18.4. Which are here. Here's figure 18.3. So in figure 18.3, the residuals are plotted across the y-axis, with time plotted across the x-axis. We said that the residuals increases with an increase in time. Hence, the residuals are correlated as they exhibit an increasing relationship with the increase in time. Whereas in figure 18.4, the residuals decreases with an increase in time, and it suggests that the residuals are inversely correlated with time. The increase or decrease in the values of the residuals enables us to diagnose whether the error variance increases or decreases over time. We could also make a diagnosis about time effects from residual dot plot. As in figure 18.4, we could see that the residuals decrease as time increases, and the experiment makes more accurate measurements over time. If we had not ordered the time in the x-axis, we would not have noticed the changes in the residual plots and detected the correlation between them. Thus, it is necessary for us to order the values in the x-axis and corresponding plot the residuals in the y-axis to get a better idea of the relationship exhibited by the residuals. Now we will go to number 27. 27 is show that nt times nt plus 1 over 12, and 18.3, which we just went over, is the sample variance of the consecutive integers 1 to n sub t. And we show this by showing that the summation from I equals 1 to n sub t, where I equals nt over nt plus 1 over 2, and we know that the summation of I equals 1 to n sub t of I squared is equal to n sub t times n sub t plus 1 times 2 n sub t plus 1 over 6. So we plug it into the SSTO, which is the summation of I squared minus the summation of I, all squared, over n sub t, is equal to n sub tau times n sub tau plus 1 times 2n sub tau plus 1 over 6 minus n sub tau squared times n sub tau plus 1 squared over 4n sub tau. We get that to equal to n sub tau times n sub tau plus 1 times n sub tau minus 1 over 12. Therefore, we know that SSTO over n sub tau minus 1 is equal to the n sub tau times n sub tau plus 1 over 12.